water is still. In the vast, shallow reaches of the Ordovician seas, the light of a younger sun filters through the surface, casting long, rhythmic shadows across the sediment. Here, nearly 460 million years ago, the first chapters of a long biological history are being written in the soft silt of the ocean floor. We drift now through this ancient world, where the air above is silent, and the life below moves with a slow, deliberate grace. Hidden within the rhythmic pulse of the tide, the first Eurypterids emerge. These are the ancestors of the sea scorpions, though at this moment in time, they are modest in size and quiet in their movements. They belong to the chelicerates, a lineage defined by specialized mouthparts. In the fossil record, these early forms appear as delicate impressions in stone, fine lines that trace the beginnings of a segmented body plan that would persist for over 200 million years. The sea floor is a tapestry of ancient life. We glide over mounds of soft sediment where trilobites leave intricate furrows as they graze. Above them, the straight-shelled nautiloids move through the water column, their buoyant chambers allowing them to hover like slow-moving clouds. Among these more established residents, the early Eurypterids find their place. Their bodies are composed of a series of hardened plates, a chitinous exoskeleton that provides both protection and a framework for movement. Each individual is divided into a prosoma, the head region, and a long, tapering opisthosoma. On the underside of the prosoma, 6 pairs of appendages move in a coordinated rhythm. These limbs are not yet the specialized paddles of their descendants. They are simple, jointed structures designed for walking upon the sea floor. Each step is light, disturbing only the finest grains of sand. In this era, the Eurypterid is a creature of the substrate, tethered to the ground by the weight of its own emerging history. The fossil evidence from this period is found in scattered deposits across the globe, from the ancient sediments of North America to the rocky outcrops of Wales. These fossils tell us that the early Eurypterids were already diversifying, adapting to the specific chemistries of their local waters. They lived in a world where the continents were gathered in unfamiliar shapes, and the climate was governed by the slow shifts of tectonic plates. As we drift deeper into this chapter of time, we observe the subtle features that define these pioneers. Their compound eyes, though primitive compared to later forms, are already positioned on the sides of the head, scanning the periphery for the movement of current and prey. The segments of their bodies are connected by flexible membranes, allowing them to curve and flex as they navigate around clusters of bryozoans and brachiopod shells. There is no haste in this world. The biological clock moves with the steady pace of mineralization. The Eurypterids are small, often only a few centimeters in length, yet they carry the genetic blueprints for the giants that will follow. They are the quiet observers of the Ordovician, surviving through the slow accumulation of time. The ocean provides a stable sanctuary, a medium that cushions every movement and carries the chemical signals of the environment to their sensory hairs. In the silence of the deep, the process of growth is governed by the cycle of the molt. To grow, the young Eurypterid must shed its restrictive shell. It finds a quiet crevice or a patch of soft mud, where it slowly pulls its soft body from the old casing. For a brief moment, it is a creature of pure vulnerability, waiting for the minerals in the water to harden its new, slightly larger exoskeleton. These discarded shells, or exuviae, are often what remain for us to find millions of years later, hollow ghosts of a life once lived. The relationship between the Eurypterid and its environment is one of total integration. They do not fight the currents, they exist within them. Their respiratory systems, comprised of simple gill tracts, pull oxygen from the water with every pulse of their ventral plates. It is a rhythmic, mechanical process, a heartbeat of the sea. They are part of a delicate food web, feeding on the organic debris that falls from the surface and providing a foundation for the larger predators of the Ordovician. As the Ordovician period draws toward its close, the environment begins to shift. Global temperatures fluctuate, and the sea levels that once provided these vast, shallow sanctuaries begin to recede. Yet the Eurypterid lineage is resilient. They have already established a body plan that is durable and adaptable. They are prepared for the transitions to come, for the Silurian seas where they will eventually rise to dominance. We leave this period as we found it, in a state of quiet equilibrium. The early sea scorpions remain nestled in the silt, their segmented tails resting against the cool mud. The fossils they leave behind are more than just stone. They are the physical memories of the ocean's early attempts at complex life. They are the ancestors of the arachnids, the cousins of the horseshoe crabs, and the architects of a long, silent reign. The sun sets over a world without forests, over an ocean that holds the only life the Earth knows. Beneath the waves, the Eurypterids continue their slow, ancient march, undisturbed by the passage of eras, waiting for the turning of the geological page. The sediment continues to fall, grain by grain, covering the evidence of their existence and preserving it for a future they will never see. In this stillness, the story of the sea scorpion has only just begun. The transition from the early Ordovician into the later stages of the period brings us to a form that is both distinct and specialized. We drift toward the genus Megalograptus, an organism that represents one of the first major structural diversifications within the Eurypterid lineage. In the cool, dim waters of the late Ordovician, these creatures moved with a purposeful, slow-motion gait, their bodies refined by millions of years of selective pressure. Their fossils, often recovered from the Soom Shale and other fine-grained deposits, reveal an anatomy that was perfectly balanced for its environment. The prosoma of Megalograptus is broad and reinforced, serving as the anchor for its most notable feature, the third pair of appendages. Unlike the simple walking legs of its ancestors, these limbs are elongated and lined with a series of long, stationary spines. These spines are not for swimming. Instead, they act as a biological rake. As the animal moves across the soft seafloor, it uses these specialized limbs to sift through the mud and organic detritus. This basket of spines allows the Megalograptus to capture small, soft-bodied invertebrates and organic particles with a gentle, sweeping motion. The body of Megalograptus is a study in segmented symmetry. Behind the head, the 12 segments of the opisthosoma taper gradually toward the rear. These segments are wide and flat, providing a large surface area that helps distribute the animal's weight across the silty substrate, preventing it from sinking. The cuticle, the outer layer of the exoskeleton, is decorated with small scales and pits, which in life housed sensory setae. These microscopic hairs detected the faintest vibrations in the water, allowing the animal to sense the approach of a cephalopod or the movement of a potential meal in the darkness. At the very end of the body lies the telson. In Megalograptus, this structure is a simple, robust spike. While it lacks the swimming efficiency of the paddles that would evolve later, it serves as a crucial tool for stability. When navigating the uneven terrain of a bryozoan reef or a cluster of crinoids, the animal can press its telson into the sediment to anchor itself against a passing current. It is a slow, methodical existence, where every movement is calibrated to conserve energy in the nutrient-rich but low-energy environment of the deep shelf. The internal world of Megalograptus was just as specialized as its exterior. Beneath the hardened plates of the ventral side, the branchial chambers worked in silent coordination. These chambers contained the gill tracts, thin layers of tissue that facilitated the exchange of gases. Because Megalograptus often lived in environments where oxygen levels could fluctuate, its respiratory system was expansive, allowing it to maintain a steady metabolic rate even when the water became still and stagnant. As we observe this creature in its natural habitat, we see it coexist with the giants of its day. The endocerid cephalopods, with their long, straight shells, glide overhead like ancient vessels. Megalograptus remains below, tucked into the shadows of the seafloor. It does not compete with the swimmers of the open water. It has mastered the benthic zone. Its compound eyes, positioned on the upper surface of the prosoma, look upward, monitoring the light as it plays across the surface of the sea, miles above. The fossil record of Megalograptus also provides a window into the colonial nature of ancient seas. Often, these fossils are found in proximity to graptolites, tiny colonial organisms that drifted in the currents. It is from these neighbours that Megalograptus receives its name, a bridge between the world of the drifting colonies and the world of the crawling chelicerates. This interconnectedness reminds us that no species exists in isolation. Each is a thread in a vast, submerged web of life. Growth for Megalograptus was a lifelong commitment to change. Through the process of ecdysis, the animal would leave behind a perfect record of its life stages. Each discarded shell preserved the exact dimensions of its spines and the precise curvature of its telson. For scientists today, these molts are a map of the animal's history, showing how it grew from a tiny larva into a formidable member of the benthic community. The preservation of these shells in the fine mud of the Ordovician floor is a rare gift of geology, allowing us to see the animal as it truly was. The era of Megalograptus eventually began to fade as the Ordovician drew to a close. However, the innovations it introduced, the specialized limbs, the sensory-rich cuticle, and the robust body plan, did not disappear. They became the foundation for the Eurypterid explosion that would characterize the Silurian period. Megalograptus was a pioneer of form, a creature that proved that the sea scorpion lineage could adapt to specific ecological roles with incredible precision. We leave the Megalograptus resting in a bed of ancient silt. The water around it is calm, the temperature steady, and the rhythm of life uninterrupted. It is a moment of prehistoric peace, a snapshot of a world where the arthropod was the master of the mud. The sediment continues to settle, burying the spines and the plates, sealing this chapter of the Ordovician in a tomb of stone, where it will wait for hundreds of millions of years to be rediscovered. The closing of the Ordovician period gives way to the Silurian, a golden age for the ancient oceans. As the massive glaciers of the previous era melt, global sea levels rise, spilling over the edges of the continents to create vast, shallow, epicontinental seas. These sun-wrought sanctuaries are warm, stable, and rich in minerals, the perfect laboratory for the Eurypterid order to reach its biological zenith. We drift now into these clear, turquoise waters, where the sunlight reaches all the way to the seafloor, illuminating a world of unprecedented arthropod diversity. In this chapter of time, the Eurypterids are no longer just members of the benthic community. They are its architects and primary residents. The fossil record from the Silurian reveals an explosion of new forms, each adapted to a specific corner of this expanding marine empire. We see species that have moved into the brackish estuaries, others that cling to the rocky edges of primitive coral reefs, and some that have begun to explore the mouths of the world's first river systems. This is a period of geographic conquest, where the sea scorpion lineage spreads across the ancient supercontinent of Euramerica. The morphology of the Silurian Eurypterids shows a refined complexity. The cuticle, the protective outer layer of their bodies, has become more specialized. In some species, it is thickened with calcium carbonate for defense. In others, it remains thin and flexible to allow for greater agility. Fossilized remains show the development of more sophisticated respiratory systems, with larger gill tracts that could extract oxygen more efficiently from the warm, shallow water. This anatomical advancement allowed Eurypterids to maintain higher levels of activity than their Ordovician ancestors. As we glide through a Silurian lagoon, we notice the change in the seascape. The seafloor is no longer just mud and silt. It is covered in thick mats of algae and the first complex reef systems built by tabulate and rugose corals. Eurypterids navigate these underwater forests with ease. Their appendages have diversified into an array of tools. Some are still used for walking, while others have flattened into the iconic swimming paddles that define the family Eurypteridae. These paddles allow for a graceful, hovering movement, enabling the animals to rise above the substrate and move through the water column with minimal effort. The abundance of food in these shallow seas supported a massive increase in population density. Fossils are often found in bone beds, or dense layers where hundreds of individuals were preserved together. This suggests that Eurypterids may have congregated in large numbers, perhaps following the seasonal availability of nutrients or gathering in sheltered bays to undergo the collective molting process. The silence of the Silurian Sea is filled with the rhythmic movement of thousands of segmented bodies, a living carpet of chitin and pulse. The Silurian also sees the rise of the first jawed fish, but they are still small and armoured, no match for the established dominance of the arthropods. In this era, the Eurypterid is the undisputed master of the shallows. They are the largest and most complex mobile organisms in many of these environments. Their presence influenced the evolution of every other species around them, forcing smaller organisms to develop better armour or burrowing behaviours to avoid detection. The chemistry of the Silurian oceans played a vital role in this expansion. High levels of dissolved minerals facilitated the rapid growth of large exoskeletons. The water was well oxygenated, supporting the metabolic needs of active swimmers. Fossilized trackways from this period, found in places like modern-day New York and Scotland, show that some Eurypterids were even venturing into the very thinnest films of water at the tide's edge. They were pushing the boundaries of the marine world, testing the limits of where an aquatic life could exist. We observe a large Eurypterus resting on a bed of brachiopod shells. Its body is perfectly still, save for the gentle ripple of its gill plates. It is a creature of immense evolutionary success, a design that has been honed by the demands of the sea. The Silurian expansion was not just about size, it was about the perfection of a body plan that could thrive in a variety of salinities and temperatures. This flexibility ensured that the Eurypterids would not only survive the changing world, but would define it for millions of years. As the sun sets over the Silurian horizon, the shallow seas remain a hive of quiet activity. The rise in sea levels has created a world of endless opportunity, and the Eurypterids have claimed it all. From the deepest lagoon to the highest tide pool, their segmented forms are a constant presence. They are the guardians of the Silurian, the quiet giants of a world that is only just beginning to realize its full biological potential. The sediment continues to fall, documenting this golden age in layers of limestone and shale, preserving the story of their greatest expansion. The water remains calm, the air above remains still, and the march of the sea scorpions continues. This was their time, a period of blue water and abundant life, where the foundation was laid for everything that was to follow in the history of the ancient oceans. We focus our lens now on the most iconic representative of this ancient lineage, the genus Eurypterus. If the Silurian was a golden age, Eurypterus was its definitive citizen. This genus is the most abundant and well-studied of all the sea scorpions, with thousands of specimens recovered from the Bertie waterlime of New York and the island of Saaremaa in Estonia. To look upon a fossil of Eurypterus remipes is to see a blueprint of evolutionary efficiency, a form so successful that it remained virtually unchanged for millions of years. The hallmark of this genus is the specialization of its appendages. While its ancestors relied largely on walking, Eurypterus moved with a dual-purpose anatomy. The first 4 pairs of legs are short and robust, tipped with small spines for traversing the seafloor. However, it is the 5th pair that defines the genus. These limbs have been modified into broad, flat, oar-like paddles. These are not merely decorative, they are powerful tools of propulsion. By rotating these paddles in a rhythmic figure-8 motion, Eurypterus could hover, dart, and glide through the water column with a precision that was unmatched by its contemporaries. The body of Eurypterus is a marvel of Paleozoic engineering. The prosoma is shaped like a rounded trapezoid, providing a streamlined leading edge as the animal moves forward. Its compound eyes are large and kidney-shaped, positioned dorsally to provide an expansive view of the world above and around it. Beneath the head, the mouth is surrounded by the gnathobases, toothed bases of the legs that acted as a mechanical mill. Because Eurypterids lacked internal jaws, they relied on these external structures to grind food before ingestion, a slow and methodical process that occurred while the animal was at rest. As we watch an individual Eurypterus navigate a shallow Silurian lagoon, we see the function of the opisthossoma in real time. The 12 segments of the tail are connected by strong, flexible muscles. During a burst of speed, the animal could tuck its legs and use a sudden contraction of the tail to propel itself forward, similar to the tail flip seen in modern lobsters. The telson in this genus is a long, straight spike. It acts as a rudder, providing vertical stability and allowing the animal to maintain a level course even when the coastal currents grow strong. The habitat of Eurypterus was specifically the hypersaline and brackish waters of the coastal margins. In these environments, the salt concentration was often higher than in the open ocean, which restricted the presence of many larger predators like cephalopods. These lagoons served as a nursery and a sanctuary. The calm, mineral-rich waters also facilitated the preservation of their delicate anatomy. When a Eurypterus died and settled into the fine lime mud, the lack of oxygen and high salinity prevented decay, allowing even the finest details of the breathing organs and sensory hairs to be fossilized. The sensory world of Eurypterus was highly attuned to the vibrations of the sea. Along the edges of its shell, specialized pits housed tactile hairs that could detect the wake of a passing fish or the shifting of the tide. This was an animal that lived by feeling its environment as much as seeing it. Its compound eyes were likely sensitive to changes in light intensity, helping it distinguish between the shadow of a predator and the flickering light of the surface. This multisensory approach allowed Eurypterus to dominate the shallow water niches, where light was abundant, but visibility could be obscured by sediment. Growth for Eurypterus followed the strict rules of all arthropods. We find many ghost fossils, empty shells that represent a moment of transformation. During ecdysis, the Eurypterus would find a quiet patch of algae and slowly extract itself from its old life. The resulting molt would often remain intact, settling into the mud as a perfect one-to-one replica of the living animal. By studying these molts, paleontologists have been able to map the entire life cycle of the genus, from tiny juveniles only a few millimeters long to mature adults reaching lengths of nearly 30 centimeters. The success of Eurypterus was not just due to its physical form, but its adaptability to changing water chemistries. As the Silurian climate shifted, these animals were able to migrate between marine and nearshore freshwater environments. This resilience is why they are found in such a wide geographic range. They were the generalists of the ancient seas, capable of surviving where more specialized species might fail. Their fossils are so prevalent in certain rock layers that these strata are colloquially known as Eurypterid beds, testifying to a time when they were the most common large animals on the planet. In the quiet of the Silurian evening, the lagoons are filled with the soft clicking of chitinous legs and the gentle swirl of paddles. Eurypterus is at home here, a master of the interface between the land and the deep sea. It represents a peak of the Paleozoic arthropod experience, a creature of balance, symmetry, and endurance. We leave it there, resting on a bed of fine white mud, its eyes reflecting the dimming light of an ancient world, a silent sentinel of a time when the sea scorpion was king. The transition from the open Silurian lagoons to the mouths of ancient rivers brings us to the estuary, a dynamic, shifting landscape where the fresh water of the land meets the salt of the sea. It is here that we observe a critical aspect of the Eurypterid life cycle. These environments, characterized by fluctuating salinities and tidal rhythms, served as vital corridors for the sea scorpion. Fossilized trackways and sediment analysis reveal that many Eurypterid species were not merely transient visitors, but were specifically adapted to thrive in these brackish sanctuaries. The estuary offered a unique set of advantages. For a segmented arthropod, the primary threat in the open ocean came from large, mobile cephalopods with sharp beaks and powerful tentacles. By moving into the shallow, murky waters of the estuary, Eurypterids entered a zone where these deep water predators could not follow. The complex network of sandbars, reed-like primitive plants, and muddy channels provided ample concealment. In this quiet, low-energy environment, the whisper of the tide was the only constant presence. Within these tidal flats, we find evidence of the Eurypterid's role as a scavenger and opportunistic feeder. The constant influx of nutrients from the land created a rich, organic soup. Eurypterids would use their walking legs to move methodically across the mud, their sensory hairs vibrating in response to the movement of small worms and early jawless fish trapped in the shallows. The ability to tolerate varying salt levels, a trait known as euryhalinity, was their greatest physiological asset. This allowed them to follow the tide inland, accessing food sources that remained out of reach for more specialized marine animals. One of the most significant events in the estuarine life cycle was the mass congregation for molting and potentially for reproduction. Fossil deposits in these regions often show a high concentration of individuals of the same size and species. Scientists have noted that the calm, sheltered waters of the estuary provided a stable environment for the hazardous process of ecdysis. Without the threat of heavy wave action or deep-sea predators, a Eurypterid could safely shed its old exoskeleton and wait for its new armour to harden in the mineral-rich, brackish water. The sediment in these ancient estuaries was a perfect medium for preservation. The fine-grained silts and clays often created anaerobic, oxygen-poor conditions shortly after burial. This prevented the organic components of the Eurypterid's shell from being broken down by bacteria or scavengers. As a result, many of the most complete specimens we have today come from these transitional zones. These fossils show the delicate ventral plates and even the internal gills in exquisite detail, allowing us to understand how these animals managed the transition between different water chemistries. As we watch a group of Eurypterids resting in a shallow estuarine pool, we notice the rhythm of their respiration. The movement of the opercular plates is slow and synchronized. In the brackish water, oxygen levels can be lower than in the open sea, but the Eurypterid's expansive gill tracts are more than capable of handling the deficit. They are masters of the slow burn, moving only when necessary, conserving their energy for the next shift in the tide. This patience was a key factor in their long-term evolutionary survival. The physical trackways left in these muddy environments, known as ichnofossils, provide a rare look at their behavior. We see paths that curve and loop, indicating a search for food, and straight paths that suggest a direct transit between different pools. The impressions of the paddles and the drag marks of the telson tell a story of weight and buoyancy. In the water, the Eurypterid was a graceful glider. On the saturated mud of the estuary at low tide, it was a heavy, deliberate walker, its body supported by the thick, saline-rich silt. This estuarine life cycle also represents a broader evolutionary theme, the colonization of new frontiers. By mastering the interface between sea and land, the Eurypterids were among the first large animals to exploit the resources of the inner coastal zone. They did not leave the water entirely, but they lived on the very edge of the terrestrial world. Their success in these brackish waters laid the groundwork for the eventual movement of other arthropod lineages toward a fully terrestrial existence, though the Eurypterids themselves would remain forever bound to the water. As the tide begins to rise, the Eurypterids in our view become active once more. They lift their prosomas from the mud, their paddles beginning to swirl as the incoming sea refills the channels. The estuary is a place of constant renewal and safety, a cradle for the sea scorpion. We leave them as they begin to drift back toward the lagoon, their segmented bodies disappearing into the murky, nutrient-rich water. The cycle of the estuary continues, a silent and ancient rhythm that has sustained the sea scorpion for millions of years. As we transition from the Silurian into the early Devonian, we encounter a shift in scale that redefines the prehistoric ocean. We drift into deeper coastal waters to observe the genus Pterygotus, a name that resonates with the concept of arthropod gigantism. In an era where most life remains small and tucked into the safety of the reefs, Pterygotus expanded its physical boundaries, reaching lengths that exceeded 2 meters. This was not a creature of the tide pools. It was a silent, massive presence of the marine shelf, a testament to the upper limits of what a chitinous exoskeleton could support. The physical presence of Pterygotus is dominated by its specialized predatory tools. Unlike the generalized walking legs of Eurypterus, the first pair of appendages in Pterygotus, the chelicerae, have evolved into elongated, powerful claws. These chelicerae are tipped with sharp, inward-curving teeth, designed to grasp and hold. Fossilized remains of these claws are often found in isolation, their size alone suggesting an animal of immense proportions. The sheer mechanical advantage provided by these joints allowed Pterygotus to secure prey with a slow, inescapable grip. The body of Pterygotus is remarkably streamlined for its size. The prosoma is broad but thin, and the opisthosoma is flattened dorsally. This pancake morphology allowed the animal to rest flush against the sea floor, effectively disappearing into the silt. When it moved, it did not rely on the frantic scurrying of smaller arthropods. Instead, it utilized a rhythmic, undulating motion of its segmented tail. The telson in this genus is no longer a spike, but has transformed into a large, flattened rudder, providing the necessary surface area to steer a body of such significant mass through the water column. Gigantism in the Devonian seas was supported by several environmental factors. The high levels of dissolved oxygen in the water and the abundance of nutrient-rich prey, specifically the armored jawless fish known as ostracoderms, provided the caloric foundation for such large growth. Furthermore, the arthropod respiratory system, with its expansive gill tracts, was highly efficient in these stable marine temperatures. Pterygotus did not need to be a fast pursuer. It was an ambush resident. It would wait, partially submerged in the sediment, its large compound eyes scanning the water above for the silhouettes of passing fish. The compound eyes of Pterygotus were among the most advanced of the Paleozoic. Fossilized lenses show a high degree of complexity, suggesting an ability to perceive depth and motion with great clarity, even in the lower light of the deeper shelf. These eyes were positioned at the front and sides of the head, giving the animal a wide-angle view of its surroundings. In the silence of the Devonian deep, these eyes were the primary sensors, guiding the massive claws toward their target with a slow, calculated precision. Despite its size, Pterygotus remained a creature of the water's buoyancy. On land, its weight would have crushed its internal organs, as the exoskeleton lacked the vertical support structures of terrestrial animals. In the water, however, it moved with a ghostly weightlessness. The fluid dynamics of its flattened body meant that it could glide long distances with a single push of its swimming paddles. This efficiency was vital for a giant, allowing it to patrol large territories without the excessive expenditure of energy. The fossil record of Pterygotus provides a unique perspective on the limits of the arthropod form. Every molt left behind by a giant was a feat of biological engineering. To shed a 2-meter-long shell required a complex sequence of muscular contractions and the absorption of water to swell the soft body out of the old casing. These giant exuviae, when found today, offer a complete map of the animal's musculature and the attachment points of its limbs. They show us that even at this massive scale, the Eurypterid remained a creature of delicate, segmented grace. As we watch a Pterygotus drift slowly over a bed of crinoids, we see the culmination of millions of years of chelicerate evolution. It is a peaceful giant, a sovereign of the Devonian shelf. It does not need the speed of the modern shark or the aggression of a terrestrial predator. It simply is. It occupies its niche with a quiet, overwhelming presence, a master of the slow-motion world of the ancient deep. The water around it remains still, the only movement the slight ripple of its gill plates and the occasional, slow sweep of its great telson. The reign of the giant Pterygothids was a specific moment in Earth's history, a window where the conditions were exactly right for the arthropod to reach its maximum expression. They represent the peak of the marine sea scorpion, a lineage that proved that with enough time and a stable environment, even the smallest walkers of the Ordovician could become the giants of the Devonian. We leave the Pterygotus as it settles back into the silt, its massive form blending once more into the shadows of the seafloor. a silent monument to the possibilities of prehistoric life. To understand the world of the Eurypterid, we must look through their eyes. In the dim, particulate-heavy waters of the Paleozoic, vision was the primary bridge between the organism and its environment. Fossilized specimens, particularly those from the Silurian and Devonian periods, have preserved the intricate architecture of the Eurypterid visual system with startling clarity. These were not simple light-sensitive patches, but highly sophisticated compound eyes, composed of thousands of individual hexagonal lenses known as ommatidia. The placement of these eyes on the prosoma tells a story of ecological specialization. In most genera, such as Eurypterus, the eyes are situated dorsally, on the top of the head, and toward the sides. This positioning allowed for a near panoramic view of the water column above and around them. In a world where light filtered down from a distant surface, being able to detect shadows and movement from above was a vital survival mechanism. These eyes functioned like wide-angle lenses, capturing a broad mosaic of the submarine landscape. Each ommatidium acted as an individual sensory unit, capturing a single point of light. Together, these thousands of points formed a mosaic image. While this visual data lacked the sharp resolution of a modern vertebrate eye, it was exceptionally sensitive to motion. The slightest flicker of a trilobite's leg or the undulating wake of a primitive fish would be immediately registered as a shift in the mosaic. This motion-first vision allowed the Eurypterid to remain perfectly still while accurately tracking the movement of everything within its visual field. Beyond the large lateral eyes, many Eurypterids possessed a second set of visual organs, the ocelli. These are two small, simple eyes located centrally on the top of the head. Unlike the complex compound eyes, the ocelli were likely used to measure light intensity and detect the direction of the sun. This internal compass helped the animals maintain their orientation in the water, allowing them to distinguish between up and down in murky or turbulent conditions. This dual system approach, mosaic vision for movement and simple vision for orientation, provided a complete sensory map. The internal structure of these eyes reveals further adaptations to the ancient environment. Sophisticated fossil imaging has shown that the lenses were composed of calcite, a stable mineral that provided a consistent refractive index. In some deep water species, the lenses were larger and fewer in number, an adaptation designed to capture as much light as possible in the darkness of the benthic zone. In contrast, shallow water species had smaller, more numerous lenses to provide better detail in the bright, sun-drenched lagoons. As we observe a Eurypterid hovering near a reef, we see how its vision dictates its behavior. The animal does not move its head. It does not need to. Its stationary eyes provide a constant stream of data from all directions simultaneously. It exists in a world of flickering light and shifting shapes, where every change in the mosaic is a signal of a changing environment. This visual system was so effective that it remained a core feature of the sea scorpion anatomy for over 200 million years, surviving multiple extinction events and environmental shifts. The preservation of these eyes in the fossil record is a rare event. It requires the rapid replacement of the delicate organic structures with minerals like pyrite or silica. When this occurs, we are granted a microscopic view of the ancient past. We can count the individual lenses and even determine the curvature of the eye's surface. These studies have confirmed that Eurypterids had some of the most advanced visual systems of any arthropod in the Paleozoic, rivaling the famous eyes of the trilobites in both complexity and utility. Vision also played a role in the social and reproductive lives of these creatures. While much remains hidden in the stone, the ability to recognize the specific body shapes and movement patterns of their own kind would have been essential for the mass congregations seen in the fossil beds. The visual signature of a molting peer or a potential mate was a chemical and visual signal that coordinated the rhythms of the colony. In the silence of the sea, these eyes were the silent communicators of intent and presence. We leave the Eurypterid now, its compound eyes reflecting the soft, scattered light of the Silurian afternoon. It is a creature of observation, a silent witness to the slow evolution of the reef. The complexity of its vision is a testament to the sophistication of ancient life, proving that even in the earliest chapters of Earth's history, the tools of perception were already finely honed. The water remains a blur of green and blue, but for the Eurypterid, it is a clear and legible map of survival, written in thousands of tiny, hexagonal windows. The strength of the Eurypterid lies not in a rigid frame, but in the harmonious coordination of its segments. As we observe these creatures drifting through the ancient currents, it becomes clear that their bodies are a masterclass in biomechanical engineering. The exoskeleton is not a single immovable shell. It is a series of overlapping plates, known as sclerites, connected by thin, elastic membranes. This architecture provides the perfect balance between the protection of a fortress and the fluidity of a silken ribbon. The body is divided into two primary regions, the prosoma and the opisthossoma. The prosoma, or the head shield, is a single, rigid unit that protects the vital organs and serves as the anchor point for all the walking and swimming appendages. Behind this shield, however, the opisthossoma begins, a sequence of 12 distinct segments that grant the sea scorpion its characteristic agility. These segments are meticulously jointed, allowing the animal to curve its body laterally or arch it vertically. In the silence of the deep, this flexibility is what allows a 2-meter-long giant to navigate the tight crevices of a primitive coral reef. This segmentation is powered by an internal network of longitudinal and transverse muscles. Fossilized attachment points on the interior of the shells show where these thick bundles of muscle once pulled against the chitin. When the Eurypterid needed a sudden burst of speed, it would contract these muscles in a wave-like motion, beginning at the head and travelling down to the telson. This rhythmic pulsing pushed the animal forward, mimicking the undulating movement of modern marine invertebrates, but with the added structural integrity of an armoured shell. The flexibility of the segments also played a crucial role in the animal's defensive behaviour. While we avoid the narrative of fear, we must acknowledge the fossil evidence of enrolled specimens. Like modern pillbugs or their trilobite neighbours, some Eurypterids were capable of curling their bodies inward. By tucking the vulnerable ventral side, where the soft gill plates and legs are located, inside the curve of the hardened dorsal segments, they could wait out periods of high-energy water movement or protect themselves from the abrasive shifting of sediment during a storm. The joints between these segments were sealed by arthrodial membranes. These membranes were composed of a softer, non-mineralized chitin that acted as a biological hinge. Because these membranes were softer than the plates they connected, they are rarely preserved in the fossil record, leaving behind the disconnected appearance often seen in museum specimens. However, the spacing between the fossilized plates tells us exactly how much flexibility the animal possessed. In the swimming varieties, the segments were more tightly packed to provide a streamlined profile, while in the walking varieties, the joints were wider to allow for a broader range of motion. The telson, the final segment of the body, functioned as the ultimate stabilizer. Whether it was the spike of Eurypterus or the broad paddle of Pterygotus, its movement was tied directly to the final 3 segments of the opisthossoma. These segments were often more slender and mobile than the forward plates, acting like a wrist that could angle the telson in any direction. This allowed for precise steering, enabling the animal to adjust its course with the slightest twitch of its tail. As the Eurypterid moves through the water, the segments slide over one another with a silent, mechanical grace. There is no sound of grinding chitin, only the whisper of the water as it flows over the smooth, overlapping plates. This design was so successful that it influenced the evolution of all subsequent chelicerates. The ability to remain armoured while maintaining total freedom of movement was a biological breakthrough that allowed the sea scorpion to remain a dominant force in the Paleozoic oceans for millions of generations. We leave the sea scorpion as it stretches its long, segmented body across a patch of sea lilies. Each plate catches the dim light, a series of shadows and highlights that trace the curvature of its form. It is a creature built for the slow, steady endurance of the deep, a testament to the power of flexibility in a world made of stone and water. The segments rest, one upon the other, in perfect alignment, waiting for the next slow pulse of the tide. At the terminal end of the Eurypterid's long, segmented body lies the telson, a structure that is as varied as the species themselves. In the study of ancient arthropods, the telson is far more than a simple tail. It is a critical instrument of balance, propulsion, and hydrodynamics. As we drift through the Silurian waters, we observe how this final appendage serves as the silent rudder for these armoured navigators. Its form is dictated strictly by the animal's lifestyle, carved by the physics of the water it inhabits. In the more common swimming genera, such as Eurypterus, the telson takes the form of a long, robust and straight spike. This lance-like structure provides vertical stability, preventing the animal from rolling as it moves through the water column. When the swimming paddles are in motion, the telson acts as a counterbalance, ensuring that the thrust generated at the front of the body is translated into a smooth, forward glide. It is a masterclass in linear stability, allowing the sea scorpion to maintain a steady course across the vast, open lagoons. However, as we move toward the giant pterygotids of the Devonian, the telson undergoes a radical transformation. Here, the spike has been flattened into a broad, horizontal plate. This expanded surface area functions like a modern elevator on an aircraft. By tilting this plate up or down, the massive animal could change its depth with minimal effort. This adaptation was essential for a creature of such significant mass. It turned the weight of the sea scorpion into an asset, allowing it to use the water's own resistance to navigate the three-dimensional space of the marine shelf. The telson was not a rigid, dead structure. Fossilized joints at the base of the telson reveal a complex arrangement of muscle attachments. These allowed the animal to flick or rotate the tail with surprising precision. In the walking Styloneurids, the telson was often used as a fifth limb or a prop. When resting on a slope of shifting sediment, the animal could press its telson into the mud to anchor itself, providing a stable platform for its walking legs to find purchase. It was an anchor in a world of constant current. Despite popular misconceptions fueled by their sea scorpion nickname, the telson of a Eurypterid was not a stinging organ. Peer-reviewed anatomical studies have confirmed the absence of any venom glands or delivery channels within these structures. The telson was purely mechanical, a tool of physics rather than chemistry. Its sharp point in some species may have served as a passive deterrent to predators approaching from the rear, but its primary function remained rooted in locomotion and stability. The diversity of telson shapes within the fossil record allows us to map the evolution of Eurypterid behaviour. We see the rudder forms in active swimmers, the spike forms in generalist explorers, and the paddle forms in the heavy ambush residents of the deep. Each shape is a signature of a specific ecological niche. By analysing the drag coefficients of these different forms, scientists have been able to reconstruct the swimming speeds and manoeuvrability of these ancient animals, proving they were far more graceful than their heavy armour might suggest. As the Eurypterid glides over a bed of seafloor algae, the telson follows in a gentle, trailing arc. It leaves a faint, straight line in the silt, a trace fossil that records the path of a life lived millions of years ago. There is no haste in its movement, only the steady, rhythmic application of biological engineering. The telson is the final note in the symphony of the Eurypterid body, a structure that brings balance to the complex, segmented whole. We leave the sea scorpion as it disappears into the murky distance, its telson the last part of it visible before it vanishes. It is a silent witness to the power of adaptation, a simple structure that allowed a lineage to conquer the currents for an epoch. The water closes behind it, still and undisturbed, as the sediment continues its slow, eternal descent to the floor of the ancient sea. As the Silurian gives way to the Devonian, a period often referred to as the Age of Fishes, the prehistoric ocean undergoes a profound transformation. The world is changing. Continental collisions are raising new mountain ranges, and the chemistry of the coastal waters is shifting as massive amounts of sediment and fresh water begin to pour into the sea from the rising land. For the Eurypterids, this transition is a testament to their remarkable resilience. While the open oceans are becoming increasingly crowded with fast-jawed vertebrates, the sea scorpions are finding new ways to endure. The early Devonian fossil record, particularly in the old red sandstone deposits of Europe and North America, shows Eurypterids moving away from the purely marine environments of their ancestors. We begin to see a rise in species that prefer the interstitial spaces, the deltaic systems, the lagoons with fluctuating salinity, and the mouths of the first true river systems. These animals are becoming specialists of the margins. Their physiology, refined over millions of years, allows them to breathe in water that would be too silt-heavy or oxygen-poor for the burgeoning fish populations. In these transitional waters, we observe the emergence of new morphological trends. The shells of these Devonian Eurypterids often appear more robust, perhaps as a response to the more turbulent, high-energy environments of the river deltas. We also see a divergence in feeding strategies. While some maintain the large predatory claws of the Pterygotus lineage, others are developing smaller, more intricate appendages suited for scavenging among the roots of the world's first primitive land plants, like Cooksonia, that are beginning to line the water's edge. The Devonian transition also highlights the Eurypterids' mastery of buoyancy and substrate. As they moved into shallower, more cluttered environments, the ability to walk effectively became as important as the ability to swim. Fossilized trackways from this era show a sophisticated gait, with the animal using its walking legs to lift its body slightly off the mud, reducing drag. This high-stepped movement allowed them to navigate through tangled mats of algae and early plant debris. They were the bridge between the deep marine past and the increasingly complex coastal future. This period was not a decline, but a redirection of biological energy. The stable, clear water lagoons of the Silurian were disappearing, replaced by a more fragmented and competitive world. Yet the Eurypterid remained a constant presence. Their compound eyes, once scanning for cephalopods in the blue deep, were now attuned to the murky shadows of the estuary. Their gills, once filtering the salt-rich waters of the open shelf, were now processing the tannin-rich waters of the coastal swamps. They were animals of adaptation, surviving through the slow, steady application of their proven body plan. As we look across a Devonian shoreline at twilight, we see the Eurypterids as they were, the enduring sentinels of a changing Earth. They have witnessed the rise of the first reefs, the birth of the first jawed predators, and now the first greening of the land. They are the link between the ancient Ordovician dawn and the complex ecosystems that will eventually lead to the modern world. Their story in the Devonian is one of quiet persistence in the face of a planet in flux. The water of the delta moves slowly, carrying the silt of the new mountains toward the sea. Beneath the surface, a segmented form rests in the shadows of a submerged log, its paddles still, its eyes watchful. The Devonian transition is nearly complete. The Eurypterids have found their new home in the margins, where they will continue to thrive for millions of years to come. The cycle of the ancient ocean continues, and the sea scorpion remains, a silent and permanent fixture of the prehistoric deep. As we move deeper into the Devonian period, we encounter a distinct lineage that has abandoned the open water for a life strictly upon the substrate. These are the Styloneurina, the walking Eurypterids. In this quiet, sun-dappled corner of the ancient shelf, the rhythmic pulse of swimming paddles is absent. Instead we hear, if only in our minds, the slow mechanical clicking of jointed legs against the stone. These creatures are the heavy travellers of the seafloor, possessing an anatomy that favours endurance and stability over the grace of flight through the water. The most striking feature of a Stylonerid is its legs. Unlike their cousins, who possess oar-like paddles, the Stylonerids have 4 pairs of long, robust walking appendages. These limbs are jointed with precision, allowing the animal to distribute its significant weight across the uneven terrain of the benthos. In the fossil record, these legs are often found preserved in a striding position, suggesting a gait that was both steady and deliberate. They do not scurry, they march, their segmented bodies held aloft by the strength of their chitinous frames. The prosoma of a styloneurid is often more narrow and elongated than that of the swimming varieties. This shape reduces resistance as the animal pushes through thickets of marine vegetation or navigates around the bases of crinoid forests. Their eyes remain positioned on the top of the head, but they are often oriented more forward, providing a clear view of the path ahead. For a walker, the texture of the ground and the presence of obstacles are the primary concerns of the day. They are the surveyors of the Devonian mud. Trace fossils, specifically the trackways known as palmicnium, provide the most intimate look at styloneurid life. These fossilized footprints show us the exact spacing of their limbs and the depth of their stride. We can see where the animal paused to investigate a scent in the water and where it turned with a slow, sweeping motion of its body. These tracks are the echoes of a journey taken 400 million years ago, a permanent record of a life lived in a world where the land was still largely empty and the sea was a crowded, vibrant theatre. The feeding strategy of the styloneurids was likely as methodical as their movement. Lacking the great crushing claws of the pterygotus, they relied on their forwardmost appendages to sift through the sediment. They were the processors of the seafloor, consuming the small organisms and organic matter that settled into the quiet pockets of the reef. This niche required patience and a sensory system tuned to the subtle chemical signals of the mud. Their world was one of touch and taste, guided by the thousands of sensory hairs that lined their legs. In the silence of the Devonian afternoon, a styloneurid moves through a grove of sea lilies. Its movement is so slow that it barely disturbs the delicate fronds of the crinoids. It is a creature of the earth, even while submerged in the sea. The buoyancy of the water provides just enough lift to make its heavy armour manageable, allowing it to navigate slopes and ridges that would be impassable on land. It exists in a state of constant, grounded equilibrium, a heavy-duty survivor in a changing world. The evolutionary path of the styloneurids demonstrates the incredible versatility of the Eurypterid body plan. By simply shifting the function of their limbs, they moved from being the masters of the water column to being the masters of the substrate. They proved that the sea scorpion was not a one-dimensional predator, but a complex family of organisms capable of filling every available role in the ancient ocean. They are the steady pulse of the Devonian floor, the walkers who saw the world change one step at a time. We leave the styloneurid as it reaches the edge of a deep underwater channel. It pauses, its long legs testing the stability of the slope, its eyes reflecting the scattered light of the reef. It is a creature of profound patience, a monument to the success of the slow and the steady. The water around it is still, and the sediment continues to fall, grain by grain, documenting the path of the walker in the eternal layers of the earth. We turn our focus now to Slimonia, a genus that represents the pinnacle of streamlined elegance within the Silurian seas. If the styloneurids were the heavy walkers of the deep, Slimonia was the swift glider of the open lagoons. Found primarily in the Lesma-Hugau deposits of Scotland, these fossils reveal an organism designed for a life of constant, fluid motion. Its anatomy is a study in reduction and refinement, where every unnecessary ridge or spine has been smoothed away to minimize the resistance of the water. The most striking feature of Slimonia is its exceptionally smooth and thin cuticle. Unlike the rugged, scale-covered armor of its relatives, the exoskeleton of Slimonia is almost glass-like in its simplicity. This lack of ornamentation suggests an animal that lived in the mid-water column, where speed and agility were more valuable than heavy defensive plating. The prosoma is narrow and tapered, shaped like a teardrop to cut through the water with minimal turbulence. The swimming paddles of Slimonia are elongated and graceful, positioned further back on the body to act as the primary engines of propulsion. When we observe the fossilized joints of these paddles, we see evidence of a wide range of motion, allowing the animal to hover with delicate precision or dart forward with a sudden, powerful stroke. The body itself is long and slender, providing a larger surface area for the attachment of the longitudinal muscles that powered its rhythmic swimming. One of the most distinctive aspects of Slimonia is its massive, expanded telson. In this genus, the tail does not end in a simple spike, but in a broad, leaf-shaped blade. This structure functioned as a high-performance rudder and a secondary source of thrust. By undulating its long, flexible body and tilting the wide telson, Slimonia could perform complex, aerial-like maneuvers under the waves. It was the master of the turn and the bank, a creature that navigated the three-dimensional space of the Silurian lagoon with the ease of a modern ray. The sensory systems of Slimonia were equally specialized for its high-mobility lifestyle. Its compound eyes were large and positioned forward on the head, providing a concentrated field of view that was essential for navigating at higher speeds. The thinness of its cuticle also likely allowed for a more sensitive tactile system, where vibrations in the water could be felt across the entire surface of its body. In the quiet blue reaches of the Silurian, Slimonia was a finely tuned instrument, sensing the heartbeat of the ocean through its very skin. The fossil beds where Slimonia is found often show a lack of other large predators, suggesting that these animals favoured specific, perhaps lower oxygen or higher salinity environments where their streamlined efficiency gave them a distinct advantage. They were the specialists of the quiet water, the ghosts of the Lesmahago lagoons. Their fossils are often found in a high state of preservation, with the delicate outlines of their thin shells perfectly imprinted in the dark, fine-grained siltstone. Despite its predatory nature, Slimonia possessed relatively small chelicerae, tucked neatly beneath its head. This indicates a feeding strategy that relied on speed and surprise, rather than the brute force of giant claws. It likely targeted small, soft-bodied organisms, using its agility to intercept them in the water column before they could find cover in the reef. It was a life of balance, a perfect equilibrium between the energy required for speed and the nutrients required for growth. As we watch a Slimonia move through our mind's eye, we see the true beauty of the Eurypterid form. It is a creature of curves and whispers, its body a silent shadow against the turquoise light of the surface. It does not fight the sea, it is a part of it, a living extension of the water's own fluid dynamics. The smooth plates of its back slide over one another with a mechanical perfection that has remained unchanged for hundreds of millions of years. We leave Slimonia as it glides into the deeper, darker reaches of the lagoon. Its leaf-shaped telson gives one final, slow sweep, propelling it into the silence of the ancient deep. It remains one of the most elegant entries in the fossil record, a reminder that the Paleozoic was not just a world of armour and spikes, but also a world of grace and streamlined beauty. The sediment continues to fall, grain by grain, sealing the legacy of the smooth cuticle into the eternal silence of the Scottish stone. To understand the endurance of the Eurypterid, we must look beneath the hardened plates of its exterior and into the hidden chambers that sustained its life. Breathing in the ancient oceans required a specialized interface between the organism and the water, a way to extract life-giving oxygen from a medium that was often heavy with sediment or fluctuating in temperature. The respiratory system of the sea scorpion was a marvel of Paleozoic biology, comprised of 5 pairs of intricate gill tracts located on the ventral side of the body. These gills were not exposed to the open water. Instead, they were safely housed within the branchial chambers, protected by a series of specialized plates called opercula. These plates acted as armored shutters, shielding the delicate respiratory tissues from the abrasive sands of the sea floor and the unwanted attention of smaller scavenging organisms. In the fossil record, we can see the internal surfaces of these opercula, which are often lined with fine, vascularized patterns, the physical fingerprints of the blood vessels that once pulsed with life. The gill tracts themselves consisted of hundreds of thin, leaf-like lamellae, stacked together like the pages of a book. This arrangement created a massive surface area in a very compact space, allowing for maximum gas exchange. As the Eurypterid moved, or even as it rested, it would rhythmically pulse its opercular plates. This movement acted as a mechanical pump, drawing fresh, oxygenated water into the chambers and expelling the carbon dioxide-rich water. It was a constant, silent rhythm, the heartbeat of the sea scorpion, measured in the slow expansion and contraction of its belly. This respiratory efficiency was a key factor in the gigantism of species like Pterygotus. For an arthropod to reach lengths of 2 meters, it required a constant and reliable supply of oxygen to fuel its massive muscle groups. The Eurypterid's gills were far more advanced than the simple diffusion systems of smaller invertebrates. They were a centralized, high-performance engine of respiration that supported a high metabolic rate, enabling the animal to engage in sustained swimming or powerful predatory strikes. The placement of the gills on the underside of the body also provided a unique advantage in the shallow, sun-wrenched lagoons of the Silurian. By keeping the respiratory organs close to the cool substrate, the Eurypterid could better regulate its internal temperature. Furthermore, the protected nature of the branchial chambers allowed some species to survive brief periods of low water conditions. While they were not air breathers, the moisture trapped within the opercular plates could keep the gills from collapsing, allowing the animal to endure until the tide returned. Fossilization of these soft tissues is exceptionally rare, occurring only in the most stable chemical environments. In sites like the Bertie waterlime, the gills have been preserved through a process of mineral replacement, where the organic carbon was slowly swapped for fine-grained minerals. These fossils allow us to count the individual lamellae and study the branching patterns of the respiratory canals. It is a level of detail that bridges the gap between a cold stone and a living, breathing animal, revealing the complex internal life of a creature that has been gone for hundreds of millions of years. In the quiet of the Silurian night, the only movement in a resting Eurypterid is the steady, almost imperceptible ripple of these plates. The animal is a closed system of armoured efficiency, perfectly synchronized with the chemistry of its world. It does not struggle for breath. It draws it in with the same calm deliberation that characterizes its every movement. The gills are the silent partners of the exoskeleton, the internal power source that allowed the sea scorpion to reign over the Paleozoic deep for an epoch. We leave the respiratory chambers now, moving back to the broad, sweeping forms of the exterior, but we carry with us the knowledge of the pulse, the rhythmic, hidden mechanics that made the sea scorpion a masterpiece of evolution. The water continues to flow, the oxygen continues to dissolve, and the gills continue their tireless work, hidden behind the shield of the ancient armour. In the quiet, lime-rich waters of the Silurian, we encounter a silhouette that deviates from the streamlined grace of Eurypterus. This is Mixopterus, a genus that represents a highly specialized branch of the Eurypterid family tree. Its fossils, most famously recovered from the Ringerike group in Norway, reveal an animal that has transformed its forward appendages into a sophisticated capture mechanism. Unlike the crushing claws of the giants or the simple walking legs of the trackers, Mixopterus possesses a basket of spines, a marvel of prehistoric biological engineering. The second and third pairs of limbs on Mixopterus are significantly enlarged and characterized by long, rigid, forward-pointing spines. These spines are not for defense. They are perfectly spaced to create a lethal cage. When the animal moved through the water, it carried these limbs tucked beneath its prosoma, ready to be deployed. Fossilized joints indicate a high degree of vertical mobility, allowing Mixopterus to strike with a sudden downward motion, pinning soft-bodied prey against the seafloor within its spiny enclosure. The body of Mixopterus follows a distinct and unusual geometry. The prosoma is broad and heavy, acting as a stable anchor for the powerful musculature required to operate its specialized limbs. Its opisthosoma, however, narrows sharply behind the midsection, ending in a tail that is remarkably flexible. The telson in this genus is curved and tapered, almost mimicking the appearance of a modern scorpion, though it remained a purely mechanical tool. This tapering body plan suggests that Mixopterus was a benthic ambush specialist, capable of maneuvering through the complex topography of a reef with ease. When we look closely at the spines themselves, we see that they are composed of thickened, mineralized chitin. They are not sharp in the way a needle is, but they are incredibly strong. In the stillness of the Silurian lagoon, Mixopterus would wait, its body partially obscured by the shadows of a stony coral or a cluster of sea lilies. Its compound eyes, positioned high on its head, monitored the light for the telltale flicker of a passing jawless fish or a smaller crustacean. Once within range, the basket would snap shut, a movement as mechanical and precise as a trap. The respiratory and sensory systems of Mixopterus were integrated into this ambush lifestyle. The animal was capable of remaining perfectly still for long periods, its gill tracts pulsing with a minimal, energy-saving rhythm. Its sensory hairs, or setae, were particularly dense along the interior of its spiny limbs, providing tactile feedback the moment a prey item made contact with the trap. This fusion of mechanical strength and sensory precision made Mixopterus one of the most effective residents of the Silurian shallows. The existence of Mixopterus highlights the ecological diversity that the Eurypterid body plan could support. It was not enough to simply be a sea scorpion. The lineage was constantly diversifying into specialized roles. Mixopterus was the specialist of the strike, an organism that proved the utility of specialized appendages over general-purpose ones. Its fossils remain some of the most visually striking in the entire Paleozoic record, a reminder of the intricate and often surprising ways that life adapts to the demands of the environment. As we watch a Mixopterus rest in the silence of the ancient sea, we see a master of its craft. It does not need to swim great distances or engage in the heavy labor of the walkers. It simply waits, a silent arrangement of spines and plates, perfectly synchronized with the slow pulse of the tide. The water around it is calm, and the sediment continues its eternal descent, eventually covering the spiny limbs and the curved tail, preserving the blueprint of this unique predator for the ages. In the silent, steady progression of a Eurypterid's life, there comes a moment of profound vulnerability and transformation. Because their bodies are encased in a rigid, mineralized exoskeleton, growth is not a continuous expansion, but a series of dramatic leaps. This is the process of ecdysis, or molting. To grow, the sea scorpion must periodically cast off its entire exterior, every plate, every spine, and every lens of its compound eyes, to emerge as a larger, softer version of itself. In the fossil record, these discarded shells are often preserved in such perfect detail that they are mistaken for the animals themselves. The cycle begins with the internal preparation of the body. Beneath the old, hardened cuticle, the animal secretes a new, flexible layer of chitin. Enzymes are released to dissolve the connection between the old shell and the living tissue, creating a thin film of fluid that acts as a lubricant. In the stillness of a Silurian lagoon, a Eurypterid undergoing ecdysis will seek out a secluded sanctuary, a crevice in a stony reef, or a patch of soft algae, where the currents are weak and the threat of disturbance is low. The physical exit from the old shell is a mechanical masterpiece. The Eurypterid absorbs excess water, increasing its internal pressure until the old exoskeleton begins to fracture. For most species, the primary split occurs along the marginal suture, a seam that runs around the edge of the prosoma. Like the opening of a hinged lid, the head shield lifts, and the animal begins the slow, rhythmic labor of pulling its soft body out of the old casing. It must extract every limb, every gill plate, and its long telson from the rigid tubes of the previous year's growth. Once free, the Eurypterid is a creature of pure vulnerability. Its new shell is as soft as silk, unable to provide support or protection. In this state, the animal is at the mercy of the water's chemistry. It must rapidly absorb minerals and water to inflate its new exoskeleton to its maximum size before it hardens. This window of time is a period of ghostly existence, where the sea scorpion is a pale, soft reflection of its former self, waiting for the calcification process to turn its flexible skin back into a suit of armor. The discarded shell, known as an exuvia, often remains exactly where the animal left it. Because it is hollow and lacks the weight of internal organs, it is easily carried by gentle currents until it settles into the mud. These molts are a primary source of information for scientists. By comparing different exuviae found in the same geological layer, researchers can track the ontogeny, the growth history, of a single species, seeing how the proportions of the limbs and the complexity of the eyes changed as the animal matured. The chemistry of the ancient ocean played a vital role in the success of the molt. High concentrations of calcium and magnesium in the Silurian and Devonian waters allowed the new shell to harden within hours. For the Eurypterid, this was a lifelong cycle of shedding and renewal, a biological necessity that dictated the rhythm of its behavior. Each successful molt was a triumph of survival, a literal shedding of the past to make room for a larger, more formidable future. We observe the discarded shell resting on the seafloor, a perfect, translucent memory of a life that has moved on. The new Eurypterid, now larger and freshly armoured, drifts away into the shadows, its colours perhaps more vibrant and its spines more sharp. The old shell remains behind, eventually to be covered by the falling sediment and turned to stone. It is a silent witness to the fact that in the ancient seas, growth always required a moment of profound surrender. In the silent, rhythmic world of the Paleozoic, the act of consuming food was a process of mechanical precision. Eurypterids, despite their often formidable size and predatory appearance, lacked the internal hinged jaws found in modern vertebrates. Instead, they relied on a sophisticated system of external processing known as nathabasic feeding. To observe a sea scorpion at rest after a successful hunt is to witness a mechanical mill in operation, where the very limbs used for walking and swimming are repurposed for the complex task of digestion. The primary tools for feeding are located on the underside of the prosoma, clustered around the central mouth opening. Each of the walking legs possesses a thickened, hardened base known as a nathabase. These bases are covered in rows of sharp, chitinous teeth and ridges. Because the legs are arranged in pairs, these nathabases meet at the midline of the body. By moving its legs in a rhythmic back and forth motion, the Eurypterid uses these jaw feet to grind, shred, and macerate its food before it ever enters the oral cavity. The process is slow and methodical. Whether the animal is processing a soft-bodied worm or the mineralized shell of a small trilobite, the mechanical action remains the same. The forward appendages, or chelicerae, are used to bring the food toward the mouth. Once the material is positioned between the nathabases, the animal engages its leg muscles to exert a powerful, crushing force. In the stillness of the Silurian lagoon, this internal grinding is a silent but constant feature of the Eurypterid's daily existence, a biological equivalent to a stone mill. Fossilized gut contents, though exceptionally rare, provide a glimpse into what these animals were processing. In some exquisitely preserved specimens, the remains of small, armoured fish and other invertebrates have been found within the digestive tract, already ground into fine fragments. This confirms that the nathabasic system was highly effective at breaking down the tough, mineralized defenses of Paleozoic prey. The Eurypterid did not need to swallow its food whole. It transformed it into a manageable paste that could be easily absorbed by its internal digestive organs. The efficiency of this system was a key factor in the sea scorpion's success as a generalist predator and scavenger. By utilizing its limbs for both locomotion and feeding, the Eurypterid minimized the need for a complex, heavy skull structure. This kept the prosoma light and streamlined for swimming, while still providing the necessary leverage for crushing. The sensory hairs, or setae, located on the legs, provided constant tactile feedback during the grinding process, ensuring that the food was properly oriented and processed. In the larger pterygotids, the feeding mechanism reached its most dramatic expression. The massive chelicerae would capture and hold the prey, while the robust nathabases beneath the head shield performed the heavy labour of dismantling it. In contrast, the smaller Eurypterus likely spent more time scavenging the organic debris of the seafloor, its smaller nathabases acting more like a sieve to extract nutrients from the mud. Despite the difference in scale, the fundamental mechanical principle remained the same across the entire order. As we watch a Eurypterid complete its meal, the movement of its legs gradually slows. The nathabases return to their resting position, and the animal prepares to move again. There is no haste, no waste, only the steady application of biological tools honed over millions of years. The sea scorpion is a masterpiece of integrated design, where the boundary between movement and nourishment is seamless. We leave it now as it lifts its body from the silt, its mechanical mouthparts tucked safely away, ready to drift back into the quiet currents of the ancient deep. To understand the rhythm of a life long extinguished, we must look beyond the silent skeletons of stone and examine the impressions left behind by the living. Trace fossils, or ichnofossils, are the preserved records of behaviour, the physical echoes of a Eurypterid's journey across the ancient seafloor. While a body fossil tells us what an animal was, a trackway tells us what it did. These markings, known as palmicnium, serve as the prehistoric blueprints of movement, capturing the exact moment a sea scorpion's jointed limbs pressed into the saturated silt of a Silurian lagoon. The formation of a trackway is a delicate coincidence of geology. The sediment must be of the perfect consistency, neither too liquid to collapse, nor too dry to resist an impression. As the Eurypterid walked, its weight was distributed through its walking legs, leaving behind a series of symmetrical, V-shaped or punctate marks. In the stillness of the shallow coastal waters, these tracks were quickly covered by a thin layer of fine sediment, sealing the gait of the animal into the Earth's memory before the tide could wash it away. When we analyse these trackways, we see a story of deliberate, measured progress. The spacing between the marks allows scientists to calculate the stride of the animal, providing a direct measurement of its leg length and body width. We see evidence of different gaits. Some tracks are narrow, indicating a focused forward transit, while others are broad and staggered, suggesting the animal was navigating a slope or resisting a lateral current. Occasionally, a long central furrow accompanies the leg marks, the unmistakable drag of the telson as it trailed behind like a heavy rudder in the mud. These tracks also reveal the interaction between the animal and its environment. In the transition zones between water and land, we find trackways that become more deeply impressed, indicating where the animal lost the buoyancy of the sea and had to support its full weight upon the substrate. Some fossils show a scrambling pattern, where the legs moved in rapid succession to climb an embankment. These are the snapshots of effort, the mechanical struggles of a creature navigating the boundaries of its world. Beyond simple walking, trace fossils record the moments of rest and feeding. Circular depressions in the silt, often surrounded by a radial pattern of leg marks, suggest a sit and wait ambush position. Here, the Eurypterid partially buried itself, leaving only its compound eyes and the tips of its limbs exposed to the current. Other markings show where the gnather bases, the toothed leg bases, were pressed into the mud as the animal processed a meal, leaving a distinct mechanical signature in the soft earth. The study of palmicnium has corrected many historical misconceptions about Eurypterid movement. By matching the trackways to the anatomy of different genera, researchers have proven that, while some were agile swimmers, others were strictly benthic walkers that rarely left the seafloor. These fossils provide a dynamic context that skeletal remains cannot, showing us the sea scorpion as a functioning, moving organism. They remind us that the Paleozoic was not a gallery of static statues, but a vibrant, busy landscape of constant motion. As we look upon a slab of fossilized mud from the Silurian, we are looking at a moment in time that has been frozen for 400 million years. The trackway leads off the edge of the stone, an unfinished sentence in the history of the sea. We can almost imagine the slow, rhythmic clicking of the legs and the soft swirl of the silt as the animal moved into the distance. It is a profound connection to a living past, a trail of breadcrumbs left by a ghost in the deep. We leave the trackways now, as the ancient tide begins to rise in our imagination. The footprints remain, hidden beneath the layers of time, a testament to the fact that every life, no matter how ancient, leaves a mark upon the world. The sediment continues to fall, grain by grain, as it always has, preserving the journey of the sea scorpion in the eternal silence of the stone. In the shifting, high-energy waters of the Silurian reefs, the streamlined forms of the open lagoon give way to a more robust and specialized geometry. This is the domain of Carcinosoma, a genus that represents a departure from the typical Eurypterid silhouette. While its relatives evolved for speed or steady walking, Carcinosoma adapted for a life of weight and concealment. Its body is a study in broad, heavy plating, a tank of the ancient benthos, designed to withstand the crushing force of the tides and the abrasive surge of coastal currents. The prosoma of Carcinosoma is notably wide and rounded, forming a heavy shield that is broader than it is long. This wide leading edge acted as a stabilizer in turbulent water, allowing the animal to remain anchored to the seafloor while the waves crashed above. Its compound eyes are positioned further forward and toward the center of the head shield than in other genera, suggesting an animal that spent a significant amount of its life partially buried in the sand, looking upward through the hazy, sunlit water for the movement of prey. The appendages of Carcinosoma are uniquely specialized for its heavy-set lifestyle. The walking legs are shorter and more powerful than those of the Stylonarids, designed for leverage rather than stride. The most distinctive feature, however, is the curvature of the body. Behind the broad head, the Opisthossoma tapers rapidly, often curving upward toward the rear. This gives the animal a scorpioid appearance, though the anatomy remains fundamentally Eurypterid. The telson in this genus is often curved and sharp, providing a final point of stability as the animal wedged itself into the crevices of a stony coral reef. The cuticle of Carcinosoma is frequently adorned with a dense pattern of scales and tubercles. These were not merely decorative, they increased the structural integrity of the shell and may have helped break up the animal's silhouette against the textured seafloor. In the silence of the Silurian, Carcinosoma was a master of the low profile. It did not swim through the water column, it occupied the spaces between the rocks, using its broad body to shield its vulnerable underside from the environment. Because of its heavy build, Carcinosoma likely relied on a sit-and-wait predatory strategy. It was a creature of the shadows, a heavy presence that waited for the ocean to bring food to its doorstep. Its respiratory system was well protected beneath its broad ventral plates, allowing it to maintain a steady flow of oxygen even when partially covered by sediment. This ability to remain stationary for long periods made it a successful resident of the reef, a niche where patience was as valuable as strength. The fossilization of Carcinosoma often occurs in coarser sediments than the fine muds of the lagoons, reflecting its preference for high-energy environments. These fossils are often thick and heavy, preserving the three-dimensional depth of the animal's broad shell. When we look at these remains today, we see an organism that chose durability over agility. It was a specialist of the reef, a creature that proved the Eurypterid body plan could be modified into a fortress of chitin and bone-like mineral. As we observe a Carcinosoma in our mind's eye, we see it wedged between two clusters of tabulate coral. It is perfectly still, its broad back matching the grey-green hue of the surrounding stone. Only the slight movement of its forward limbs, testing the chemical signature of the water, betrays its life. It is a creature of mass and silence, a silent guardian of the reef's edge. The water around it is turbulent, filled with the debris of the sea, but the Carcinosoma remains unmoved, a monument to the power of a heavy-set design. We leave it there, as the ancient sun sets and the tides pull back toward the deep. The broad plates of its shell are covered by a thin layer of sand, hiding it from the world and preserving its form for the millions of years to come. The cycle of the reef continues, and the Carcinosoma remains a silent, heavy witness to the enduring success of the sea scorpion lineage. The transition from a living, breathing organism to a silent artifact of stone is a journey of chemical fortuity. For a Eurypterid to endure through 400 million years of geological upheaval, it must bypass the natural cycle of decay and scavengers. Most organisms that perish in the sea are reclaimed by the ocean. Their soft tissues are consumed by bacteria, and their shells are dissolved by the acidity of the water. However, in rare and quiet pockets of the ancient world, the chemistry of the environment aligned to freeze these creatures in time. The primary requirement for this preservation is anoxia, the absence of oxygen. When a Eurypterid settled into the fine lime mud of a Silurian lagoon, or the silty bottom of a Devonian delta, it needed to be buried quickly. If the sediment was deep enough and the water above was still enough, oxygen could not penetrate the layers. Without oxygen, the aerobic bacteria that typically break down chitin were unable to function. In this oxygen-starved tomb, the decay process slowed to a whisper, allowing the delicate structures of the gills, the eyes, and even the muscle attachments to remain intact. As the millennia passed, the organic carbon of the Eurypterid shell underwent a slow, atomic transformation. Through a process known as permineralization, mineral-rich groundwater seeped through the porous sediment and into the empty spaces of the exoskeleton. Depending on the local chemistry of the water, different minerals took the place of the original biological material. In many cases, calcium carbonate replaced the chitin, turning the shell into a dense limestone. In others, silica or iron pyrite, fool's gold, crystallized within the cells, creating a gleaming metallic replica of the animal. The most exquisite Eurypterid fossils are found in Lagerstätten, a German term for sedimentary deposits that exhibit extraordinary fossil richness or completeness. The Bertie waterlime in New York is perhaps the most famous of these. Here, the water was so hypersaline that very few other organisms could survive, meaning there were no scavengers to disturb the remains. The sediment was composed of a fine, lime flour that captured the impression of the animal with the precision of a photographic plate. When we split these stones today, we see the dark, carbonized film of the sea scorpion's cuticle, as thin and detailed as it was on the day it died. The color of a Eurypterid fossil is itself a chemical signature of its history. Darker, blacker fossils indicate a high concentration of carbon, suggesting the animal was buried in a low-energy, swamp-like environment where organic matter was abundant. Lighter, tan or grey fossils often come from marine limestones, where the shell was replaced by calcite. Occasionally, the preservation is so perfect that the original iridescent sheen of the chitin can still be seen, a structural colour that has survived the crushing weight of mountains and the passage of eons. Geological pressure also plays a role in this chemical story. As layers of sediment piled miles high above the fossil, the heat and weight flattened the three-dimensional animal into a two-dimensional silhouette. This process, known as compression, is why most Eurypterid fossils appear as thin, papery films. However, because the mineral replacement was so thorough, even these flattened remains can be studied under a scanning electron microscope to reveal the microscopic scales and sensory pits of the original skin. We stand today in the silence of a museum gallery, looking at a stone that was once a creature of the tide. The chemistry that preserved it is a testament to the stability of the Earth's deep cycles. The sea scorpion did not simply vanish, it was translated into a different language, the language of minerals and ions. It is a masterpiece of geological patience, a life that was saved from oblivion by the very mud that claimed it. The sediment continues to fall, and the minerals continue to seep, ensuring that the legacy of the Eurypterid is written in a medium that outlasts the oceans themselves. The history of the Eurypterid is not merely a biological one. It is a story tethered to the slow, colossal movement of the Earth's tectonic plates. During the Silurian and Devonian periods, the world did not look as it does today. The continents were gathered into two major landmasses, Gondwana to the south and the smaller, rising continent of Euramerica to the north. It was in the shallow, tropical shelf seas surrounding Euramerica, the old red sandstone continent, that the Eurypterids found their most enduring sanctuaries. As we look at a map of this ancient world, we see that the lands we now call North America, Greenland, and Europe were joined together. The equatorial location of these landmasses created a climate of eternal summer. The waters were consistently warm, supporting a high rate of metabolism and rapid mineral growth. This geological configuration provided a continuous coastline of thousands of miles, a massive highway of shallow lagoons and estuaries that allowed the Eurypterid populations to spread and diversify without the barrier of deep, cold oceans. The drifting of these plates was a slow process, but its effects on the Eurypterid habitat were profound. As Euramerica moved, the the sea levels fluctuated, creating and destroying the shallow water niches these animals relied upon. When plates collided, they raised mountains, the Caledonian and Acadian orogenies, which in turn shed massive amounts of sediment into the sea. This influx of silt created the very deltas and brackish marshes that the later Eurypterids would come to dominate. The geology of the planet was, in a very literal sense, the architect of their evolution. The distribution of fossils today is a direct result of this continental dance. A researcher finding a Eurypterus in New York is looking at a biological cousin to a specimen found in the mountains of Scotland or the islands of Estonia. During the Silurian, these locations were mere miles apart, separated only by quiet, sunlit lagoons. The fact that we find these identical forms across a modern ocean is one of the most compelling pieces of evidence for the theory of continental drift. The sea scorpion is a traveller across time, but it was also a passenger on the moving plates of the Earth. Habitat specialization was the key to their longevity. As the continents shifted, some Eurypterids became endemic, or unique to specific local basins. The isolation of these water bodies allowed for the development of highly specialized forms, such as those found in the Lesmahago of Scotland. These isolated populations were experiments in evolution, testing new body shapes and feeding strategies in response to the unique chemistry and predators of their local sea. When the sea levels rose again, these populations would mingle, spreading their genetic innovations across the Euramerican shelf. However, the very drift that sustained them also brought new challenges. As the continents moved away from the equator toward the end of the Devonian, the water temperatures began to drop. The stable, warm lagoons were replaced by more seasonal and turbulent environments. The Eurypterids, ever the masters of the margins, began to retreat into the freshwater river systems and inland swamps that offered more stable temperatures. Their habitat was shrinking, being squeezed between the cold, open oceans and the drying land. We observe the Eurypterids now as they navigate these changing coastlines. They are unaware of the plates beneath them moving at the speed of a growing fingernail, but they are entirely dependent on the results of that movement. The depth of the water, the salinity of the bay, and the temperature of the current are all dictated by the position of the land. They are the inhabitants of a moving world, surviving through their ability to shift with the shifting Earth. We leave the continents as they continue their slow, inevitable crawl across the globe. The shallow seas of Euramerica are beginning to close, and the age of the sea scorpion is transitioning into its final chapters. But for millions of years, the alignment of the Earth's crust provided the perfect stage for the Eurypterid to flourish. The sediment continues to fall, grain by grain, recording the position of the continents and the presence of the animals in a dual history of stone and life. As we leave the Devonian and enter the Carboniferous period, the world's atmosphere grows thick with oxygen, and the continents begin to buckle into the vast supercontinent of Pangaea. In the inland freshwater swamps and stagnant river systems, we encounter a giant that redefines the limits of the Eurypterid body plan, Hibbertopterus. This is not a sleek swimmer or a sharp-clawed hunter. Hibbertopterus is a massive, heavy-bodied creature of the mud, an animal that moved with the slow, crushing weight of a living tank across the floor of the coal-forming forests. The morphology of Hibbertopterus is an adaptation to a very specific lifestyle known as sweep feeding. Reaching lengths of nearly 2 meters and possessing a broad, hemispherical prosoma, it lacked the predatory chelicerae of the Pterygotus. Instead, its forwardmost limbs were covered in a dense, specialized array of fine spines and sensory organs. As the animal moved through the murky, nutrient-rich silt of the Carboniferous swamps, it would use these limbs to sweep through the mud, sifting out small invertebrates, larvae, and organic debris with the precision of a biological sieve. This feeding strategy required a massive amount of physical support. Because Hibbertopterus lived in shallow, often semi-aquatic environments, it could not rely entirely on the buoyancy of the sea to support its weight. Its walking legs were thick and pillar-like, designed to carry its heavy exoskeleton over the soft, yielding substrate of the swamp. Fossilized trackways found in Scotland, extending over 6 meters in length, show the rhythmic, heavy footprints of this giant, accompanied by a broad central furrow where its massive belly and telson dragged through the mud. The respiratory system of Eurypterus was equally specialized. To survive in the stagnant, often oxygen-poor waters of the Carboniferous swamps, it possessed expansive branchial chambers. These gills were protected by reinforced ventral plates that kept the delicate respiratory tissues from being clogged by the fine coal silt. Some researchers suggest that the robust nature of these chambers might even have allowed Eurypterus to survive brief periods of exposure to the air, moving between pools in the humid, oxygen-rich environment of the forest floor. The sensory world of this giant was tuned to the vibrations of the mud. While its compound eyes remained functional, its primary connection to the world was through the thousands of sensory hairs, setae, that lined its sweep-feeding limbs. In the dark, tea-coloured waters of the swamp, vision was a secondary tool. Eurypterus felt its way through the world, its limbs acting as sensitive antennae that could detect the chemical signature of food or the distant, heavy vibrations of another giant moving through the trees. Despite its size, Eurypterus was a creature of profound patience. Its metabolic rate was likely slow, allowing it to thrive on the abundant but low-quality nutrients found in the swamp sediment. It was a master of the slow burn, a biological machine designed for the steady processing of the Carboniferous landscape. In the silence of the ancient forest, the only sound of its presence would have been the soft, wet squelch of its walking legs and the rhythmic pulse of its breathing plates as it sieved the earth for life. As we watch a Eurypterus disappear into the shadows of a giant club moss forest, we see the ultimate expression of the marginal specialist. It took the Eurypterid body plan into the heart of the continents, adapting to a world of fresh water and mud. It was one of the last great experiments in Eurypterid gigantism, a creature that proved that even as the oceans changed, the lineage could find a way to endure in the quiet, dark corners of the land. The sediment of the Carboniferous, which would one day become the great coal seams of the world, slowly covers the tracks of the giant. Grain by grain, the history of the sweep feeder is sealed into the earth, a silent record of a time when the sea scorpion walked among the roots of the first great forests. The world of the Carboniferous is a landscape of profound transition, a period where the boundaries between the water and the land become blurred. As we drift away from the open coastlines, we find ourselves deep within the interior of the supercontinent, submerged in the tea-coloured waters of the great coal swamps. The air above is heavy and thick, saturated with a concentration of oxygen far higher than the modern world, while below the surface, the water is still, warm, and laden with the organic tannins of fallen vegetation. In this environment, the Eurypterid lineage finds a final, unique sanctuary. The towering lepidodendron and sigillaria trees, giant lycopsids that reach 30 meters into the sky, drop a constant rain of spores, leaves, and woody debris into the shallow basins. This accumulation of organic matter creates a complex, labyrinthine world of submerged roots and decaying peat. For a creature with a segmented, armoured body, these swamps are a maze of opportunity. The Eurypterids that thrive here have traded the vast horizons of the sea for the dense, nutrient-rich shadows of the forest floor. The water chemistry of these swamps is distinct from the alkaline oceans of the past. The decay of vast amounts of plant matter creates an acidic, low-oxygen environment. While many marine species would find these conditions lethal, the Carboniferous Eurypterids have evolved to manage the chemical stress. Their branchial chambers are reinforced, and their metabolic rates have slowed to a measured, rhythmic pace. They move with the deliberate patience of an animal that has no need for haste, navigating the stagnant pools where the only current is the slow percolation of rainwater through the peat. This environment also supports a new ecosystem of competitors and neighbours. We observe giant, primitive amphibians and early reptiles beginning to explore the edges of these pools, while in the water, the Eurypterids coexist with massive freshwater fish and the first true freshwater crustaceans. However, the high oxygen levels of the Carboniferous have also allowed for the rise of giant terrestrial arthropods, such as the 3-meter-long Arthropleura. In this age of giants, the Eurypterids remain the silent aquatic counterparts to the giants of the land, filling the niche of the large-bodied benthic scavenger. The preservation of fossils in these swamp environments is fundamentally different from the marine limestones of the Silurian. Here, the Eurypterids are often found within siderite nodules, hard, iron-rich stones that formed around the animal shortly after it was buried in the mud. When these nodules are split, they reveal a high-contrast impression of the sea scorpion, often showing the delicate details of the legs and the fine texture of the cuticle. These fossils are frequently associated with the imprints of ferns and horsetails, providing a direct geological link between the animal and the forest that sheltered it. In the stillness of the Carboniferous afternoon, the swamp is a theatre of soft, wet sounds. The splash of a lungfish, the distant hum of a giant dragonfly, and the slow, rhythmic pulse of a Eurypterid's breathing plates. The high atmospheric pressure and dense humidity mean that the water evaporates slowly, maintaining stable water levels even during periods of low rainfall. This stability allowed the Eurypterid lineage to persist in these inland refuges long after the shifting continents had destroyed their original marine habitats. As the sun sets through the dense canopy, casting long orange light across the surface of the stagnant pools, we see the Eurypterid as it truly is, a survivor of the ages. It has moved from the primordial Ordovician seas to the very heart of the world's first great forests. The sediment that will one day become the coal seams of the industrial world is already beginning to settle, grain by grain, covering the segmented shells and the trailing trackways. The swamp is a cradle of preservation, a silent vault that will hold the history of the Carboniferous sea scorpion for 300 million years. We leave the dark waters now, moving toward the twilight of the lineage. The swamps are vast, the oxygen is rich, and for a moment, the world feels as though it will remain this way forever. But the earth continues to shift, and the coal forests are merely another chapter in the long, slow journey of the sea. While the giants of the Carboniferous swamps captured the scale of the era, the true story of endurance belongs to a much more modest genus, Adalophthalmus. In the shifting landscape of the late Paleozoic, this genus emerged as the most successful and widespread of the final Eurypterid lineages. Its fossils have been recovered from nearly every corner of the supercontinent Pangaea, from the coal basins of North America and Europe to the remote sediments of Siberia. Adalophthalmus was the ultimate generalist, a survivor that thrived while the more specialized giants began to fade. The morphology of Adalophthalmus is characterized by a return to basics. It possessed a streamlined, medium-sized body, usually averaging between 10 and 20 centimeters in length. The prosoma was semicircular and robust, housing compound eyes that were positioned closer to the center of the head shield than in its Silurian ancestors, a feature that gave the genus its name, meaning hidden eye. This placement likely protected the visual organs from the abrasive silt of the fresh water and brackish environments it frequented. One of the keys to the success of Adalophthalmus was its physiological flexibility. It was among the first Eurypterids to fully commit to non-marine habitats. While earlier lineages were tethered to the chemical stability of the ocean, Adalophthalmus mastered the unpredictable waters of river deltas, lakes, and inland drainage basins. It could tolerate high levels of sediment and varying mineral concentrations, allowing it to occupy niches that were too stressful for other aquatic arthropods. It was the pioneer of the new waters, trailing behind the retreating seas as the continents closed together. The appendages of Adalophthalmus remained versatile. It retained the classic swimming paddles of the Eurypteridae family, but its walking legs were reinforced for movement across soft, muddy substrates. This dual-mode locomotion allowed it to navigate the complex, cluttered floors of the Carboniferous and Permian waterways. Whether it was drifting through a stagnant pool or marching across a riverbed in search of organic debris, Adelophthalmus moved with an efficiency that favoured energy conservation over raw power. In the silence of a late Carboniferous riverbank, we observe the resilience of this lineage. These animals were not the apex predators of their day. They shared their waters with large, primitive sharks and sprawling amphibians. Their survival strategy relied on being inconspicuous and adaptable. They were the cleaners of the late Paleozoic, processing the organic rain of the forests. By filling a stable, mid-level niche in the food web, Adelophthalmus avoided the extreme pressures that often drive specialized giants toward extinction when the environment shifts. The fossil record of Adelophthalmus is remarkably continuous. Because they lived in environments where sedimentation was rapid, such as flooding river systems, their remains were frequently buried and preserved. These fossils often appear in large numbers, suggesting that, like their Silurian predecessors, they may have congregated in sheltered areas for molting. The consistency of their body plan across millions of years is a testament to the perfection of their design. Once they found a form that worked in the freshwater world, they adhered to it with remarkable fidelity. As we look toward the Permian period, Adelophthalmus remains the lone representative of a once vast order in many regions. It is the thread that connects the ancient marine origins of the sea scorpion to its final, quiet conclusion in the heart of the continents. It reminds us that in the long history of life, the most dramatic forms are often the first to vanish, while the small, adaptable generalists are the ones who carry the legacy forward. The water of the inland basin is still, and the sediment continues to settle, grain by grain, over the segmented form of an Adelophthalmus. It is a creature of the shadows and the silt, a silent survivor that saw the world change and simply changed with it. We leave it there, resting in the mud of a world that is becoming increasingly dry, a final, resilient echo of the great sea scorpions of old. In the murky, tannin-stained waters of the late Paleozoic, vision often surrendered to the power of touch. The cuticle of a Eurypterid was not merely armor. It was a sophisticated sensory organ, covered in thousands of microscopic pits and hair-like structures called setae. These sensors allowed the animal to feel the chemical composition of the water and detect the faintest vibrations from a passing predator or prey. Every movement in the swamp was registered as a tactile map, a silent language of ripples and scents that guided the sea scorpion through the darkness. As the Devonian period drew to a close, the marine world faced a series of environmental pulses that reshaped the ocean's chemistry. Fluctuating oxygen levels and cooling temperatures led to the decline of the great reef systems that had sheltered the pterygotids. The fossil record shows a gradual thinning of the marine giants as the lineage began to funnel toward the freshwater refuges of the inland basins. These extinction events were not sudden crashes, but a slow narrowing of opportunity, favouring those who could endure the changing breath of the sea. During the Carboniferous, the high atmospheric oxygen levels supported a world of oversized arthropods, both on land and in the water. Eurypterids lived alongside the colossal Arthropleura and giant dragonflies, occupying the aquatic niches of the great coal-forming forests. This era represented a final burst of biological exuberance, where the abundance of nutrients and oxygen allowed the sweep feeders to reach massive proportions. It was a time of strange and heavy shadows, where the segmented body plan reached its physical maximum in the humid stillness of the swamps. The late-stage Eurypterids, particularly the hardy Adelophthalmus, developed a remarkable tolerance for low-oxygen environments. Their expansive gill chambers were shielded by reinforced plates, allowing them to extract oxygen from the stagnant, sediment-heavy waters of the inland river deltas. This resilience allowed them to survive in habitats that were hostile to most other aquatic life. They became the masters of the margins, finding safety in the very places where the water was too thick and the oxygen too thin for their competitors to follow. The Permian period brought a global shift toward aridity as the supercontinent Pangaea became a land of vast deserts and shrinking water systems. The inland swamps and river basins that had sheltered the last sea scorpions began to evaporate or become increasingly isolated. Fossil evidence from this time is rare, showing a lineage that was being compressed into smaller and smaller geographic pockets. The stable water cycles that had persisted for millions of years were breaking down, and the environmental safe zones were vanishing into the dust of a warming world. The final chapters of the Eurypterid story are written in the late Permian sediments of Russia and South Africa. These last fossils are small, specialized, and isolated, a quiet conclusion to a lineage that once dominated the global oceans. By the time of the Great Permian extinction, the once diverse order had been whittled down to its last resilient genera. When the final environmental collapse occurred, the last of the sea scorpions disappeared from the fossil record, leaving behind a legacy that spans over 200 million years of Earth's history. Though the sea scorpions are gone, their influence remains etched in the evolution of the Earth's arthropods. They pioneered the body plans, respiratory systems, and sensory structures that would eventually allow their cousins, the arachnids and horseshoe crabs, to thrive in the modern world. Their history is a testament to the power of adaptation and the slow, steady rhythm of the ancient deep. As the sediment of the modern world continues to settle, we look back through the stone at a time when the segmented giants ruled the water, a silent, enduring memory